today we will read the fields, one algebraic systems, and in particular our emphasis will be on finite fields, because as real life applications there are numerous application areas that where finite fields are used, particular that cryptography and the coding theory, where mainly the finite fields are used. So, first we read that the field. Since already we have read the number of algebraic systems, and there we have seen that in the general properties that they hold. Now, based on those properties that we try to define the algebraic system field. So, if field F and normally a field is also with two binary operations like ring. So, we write that as if the addition and the multiplication is a set of elements with two binary operations like ring that we have read last day. Say addition and multiplication, but as already we have read, we have seen that this addition and multiplication may not be the ordinary addition and multiplication. And such that if ABC are the elements of F, then the following axioms are satisfied. If we remember that these axioms are the properties that are the mainly the closure property, the associative, the identity element must be there, and when we are considering two binary operations, then distributive property must be whole. So, if we see those properties, say for addition we can write, that means for addition operation the properties are say closure, then it has the associative, then it has additive identity should be there, then it must be commutative, and additive inverse exist. So, this is when we consider the addition operation or and addition operation, that is my, here we have considered it is plus. Now, similarly, if I consider the, because field on field there are two operations are there. So, if I consider the multiplication operation, for multiplication operation, then I should have the closure, that means it should be closed under multiplication, then associative with respect to the multiplication operation, then multiplicative identity should be there, now the distributive property should be there, so it should be distributive. Now, if the multiplication is commutative, then it can be a commutative ring. Now, we can also see that integral domain, that means if it is multiplicative identity and the no divisors, that means if I add another property, we have seen that multiplicative identity and no divisors, no zero divisors, then it is the integral domain. Then it is, so we have seen that if it is say additive property, we can write that it is A multiplicative M. So, if it is A1 to A6 it holds, then I can write M6 to M7 and M9, M10, then it is, I can tell this is commutative ring. That we have read last day. And now, if I add two more, that M8, that multiplicative identity, and the M11, the no zero divisors, then I can tell that this is the integral domain. This is the integral domain. Now, see, for when we have considered the addition operation, we have considered that additive inverse, but when we have considered all the multiplication operation, the properties which are must be obeyed under multiplication, say here closure, associative and multiplicative identity for integral domain, it can be commutative, and distributive when both addition and multiplication we have considered. So, distributive for both addition and multiplication, but multiplicative inverse we have not considered. So, here for the field that in addition, that must multiplicative inverse it must satisfy it. So, we can write the additional thing that M12 is the multiplicative inverse exist. So, over the properties satisfied by the commutative ring and the integral domain, if we see that multiplicative inverse exists, then it is a field. So, what is multiplicative inverse? That means if A belongs to F, the field, and say multiplicative identity is E, this E is the multiplicative identity. So, which is for normal multiplication or ordinary multiplication it is 1. For ordinary multiplication identity is 1. Then there must exist an element A inverse such that A inverse in multiplication if I take equal to A inverse equal to the multiplicative identity E equal to maybe equal to 1 for ordinary multiplication. So, this A inverse must exist for the field, and then we call that this is a field. Now, if we remember, and when it is finite field that if the order of the field is finite, that means the number of elements in the set are finite. So, it is finite field if the order of the field is finite, and order means we know order is the size of the set, that means the number of set of elements. Okay. And as I already mentioned that infinite field is of very less use. Actually, the real life applications like cryptography, coding theory, the finite fields are used. So, mainly in our lectures we will be concentrating on the finite fields and their properties. So, if we remember the in the lecture that or when we have read the ring, we have taken some examples that addition and multiplication modulo, we have taken addition and multiplication modulo 8, one examples we have seen. And what we have shown that under multiplication modulo 8, it is a ring, but when we have seen the operations, the addition and multiplication modulo 8, then we have seen that it is the multiplicative inverse does not exist for all the elements. If we remember what will be the set when we are taking the modulo 8, normally we have read that Z. Now, we give the notation that it is a Z8 is the set. What is Z8? Because if I take the modulo 8, that means it is nothing but the remainder when some number is divided by 8. So, remainder can be 0 to 7, 0, 1, 2, 3, 4, 5, 6, 7. So, this is the set Z8, and we have seen that Z8 and then the addition modulo 8 and the multiplication modulo 8, we have taken this here plus and star are the addition and multiplication modulo 8. Now, when we have written that all the or tabulated all the additions and the multiplication modulo 8, we have seen that if we remember that only since these are my set elements. So, some set A, if I write that this is 0, 1, 2, 3, 4, 5, 6, 7, then we got that additive inverse. We got that additive inverse. Additive inverse for 0 it is 0, because for additive identity is 0. This is 7, this is 6, 5, since modulo 8 is 0. So, this is 4, 3, 2, 1. When we have taken the same thing for the or multiplicative inverse, here multiplicative is that modulo 8 multiplication. Then we have seen that for 0 normally we do not get, because 0 then there should not be 0 divisors. Then for 1 we get it is 1, for 2 we did not get any multiplicative inverse, for 3 it is 3, for 4 we did not get, for 5 it is 5, for 6 we did not get any inverse, for 7 it is 7. If we remember again, then it is for say 5, this is we know that 5 into 5 modulo 8 equal to 25 mod 8 and this equal to 1, remainder is 1. So, similar way we can get the 1 and 7. Now, see, and the conclusion we have made that if this A, if we remember that conclusion was that if A and n, when we are taking modulo n or n multiplication, then A and n are relatively prime, then we get the then multiplicative inverse exist. For Zn, this is for Zn. So, and since here 2, 4 and 6 are not relatively prime to 8, so we did not get, but here say 3, 1, 3, 5, 7, they are relatively prime to 8, So, multiplicative inverse exist. So, that is why the ring under modulo addition or modulo multiplication, or if we take the modulo 8 multiplication, that means Z8 was not a ring, or Z8 is not a ring. Now, if it is a field, that multiplicative inverse must exist. So, if I consider the n as a prime, so we consider consider n as a prime. Then what will happen? Say if it is Zn, or I write n equal to p, normally that is the convention. So, we write Zp. So, if it is Zp, then Zp the set will be 0, 1, 2, 3 and up to p minus 1. Then what is the relation between all these elements to p? Since p is a prime, since p is prime, so all the elements of Zp are relatively prime to p except 0. We do not normally we consider that 0. So, relatively prime to p, that means I can take if A belongs to Zp other than 0, then A and n are relatively prime. A and n are relatively prime. So, A and p are relatively prime. Then now if I do the modulo p addition and multiplication, modulo p addition and multiplication, that means the set I take the Zp and then plus, and last day we have given this notation as the star, that modulo addition under this is plus and star or modulo p or mod p addition, mod p addition and multiplication. Then it must be a field. So, we have considered the p and Zp, and so that the set becomes 0 to p minus 1 since p is prime. So, all the elements are relatively prime, and then the according to that example we have seen that it must be, we must get the multiplicative inverse. Now, we take one example that where we take the Z7, that means we consider p equal to 7 and the plus and star we give the modulo 7 addition and multiplication. Now, if we tabulate the addition modulo 7, so we first see the addition modulo 7. It will be only 7 elements. and modulo 7. So, if we remember, it will be same, because addition will be similar. 6 plus 1 7. So, modulo 7 it is 0. Again 7 modulo 7. It is 5, 6, now it will be modulo 7. So, it will be giving 0, 1, 2, 3, 4, 6, 0, 1, 2, 3, 4, 5. So, addition modulo will be 7, addition modulo 7, this table will be. Now, if I consider the multiplication modulo 7 on ZP. Now, since 0 multiplied by any element will be 0, now it will be similarly it is multiplied by 1, this is because multiplicative identity is 1. Now I have to take that A into B modulo 7. So, 2 into 2, 2 into 2 4, 4 modulo 7 is 4, 6 modulo 7 is 6, but 8 modulo 7 will be 1. Similarly, 10 modulo 7 will be 3 and 12 modulo 7 is 5. So, what lastly we have done modulo 8, now we are doing modulo 7. Then it is 0, 3, 6 modulo 7, 2, then it is 5, 12, 15, so it is 1, now 18, so this becomes 4. Now 0, 4, 0, 4, 8, so it is 1, then 12, it is 5, 16, it is 2, 16 modulo 7, remainder 2, then 20, so it is 6, then it is 3, 5 modulo 7, 5, 3, 1, 6, 25, so it is 4, then 30, so it is 2, 6 modulo 6 0, 6 modulo 12, so it is 5, 4, 24, then 30, so 2, then 36, so it will be 1. Now, we observe some of the scene. First thing is, except 0, we are getting multiplicative identity for each element 1, because since multiplicative identity is 1, so we are getting A inverse equal to 1 for each or for all A belongs to F ZP. Here it is, I should write that for A belongs to Z7. So, for each element of Z7 I am getting, and this is for other than 0. So, multiplicative inverse exists. Since lastly we have seen that for, or when we have discussed that multiplicative inverse exists for other properties, when we have taken that addition modulo 8 and multiplication modulo 8, that for all properties that we have, or the axioms that we have defined for field should follow, that closure, associative, additive, identity, it is a commutative, and then for since it is a commutative ring, we have shown that it is also integral domain. So, up to all these properties for addition, these A1 to A6, for multiplication for M6 to M7 commutative ring, then it is integral domain, everything is satisfied. Now, what we show that only this M12, that multiplicative inverse, that now we show that when we are taking that a prime number, that means when Z7, 7 is a prime, then multiplicative inverse exists. Since all the elements of ZP, or in this case Z7, it is relatively prime to P. So, we conclude that our under addition modulo P, addition and multiplication, these are two binary operations, multiplication modulo P, where P is prime, the on ZP, ZP is the set 0 to P minus 1 is a field, and this is a very good observation, and based on that actually we will be forming that prime field. So, normally when P is prime, we call that it is a prime field, it is a prime field, okay, is a prime field. So, on prime field, so ZP is a prime field, and operation is, and will mainly the next lectures will be considering this prime field and the extension field, that is ZP and some ZP n, that means when this is P to the power n, the set of elements are 0 to P to the power n. So, mainly our focus is on these two fields we will be discussing. So, in this lecture we have seen that how very basic concepts, that how the ZP with the two binary operations, the modulo operations, addition modulo P and multiplication modulo P, how they are forming a field and how we are defining the prime field, and then this P to the power n we call that is extension field, and mainly we will be concentrating on the studies of these two fields.